algebra. Just for fun, let's get a little crazy here. We've done, you've graphed lines before. You graphed them in pre-algebra and algebra. You've been graphing them all your life. So let's just try our principles on plain old lines. As I promised, these principles are good forever and ever and ever. On a Monday, they're good. On a Tuesday, they're good. On a Saturday, they're good. By land, by sea, forever and ever, the principles are good. So they must be good on lines, right? Let's check it. Suppose you wanted to graph, I don't know, something a little bit crazy. Say like 3x, no. 3y is equal to negative, let me think, negative x. Yeah, take that. So look at the y. The y got replaced. Oh, by the way, we graphed the plain old line, y equals x, and we make a little boundary box to fit it nicely. A good boundary box will be useful if it has some corners where you can see that the graph goes through it, so that you can replicate that when you make your new box. So this particular box, the line fits nicely because it goes through the lower left and upper right hand corners. And I can make this, because y equals x, I can make this any size I want. So let's go with 6. What does that make y? Well, that would make y 6 if x is negative 3. No. Negative 6, then if y is negative 6, x is also negative 6. Right, I'm looking at the equation here. Whatever x is, y is the same thing. So it goes through these points. I chose 6 because it's divisible by 3, just to make the math easier. Okay, let's get to it. If you replace y with 3y, what does that do to the graph? Remember, if you replace y with any constant times y, then every y has to be multiplied by the reciprocal. So every y has to be multiplied by 1/3. Multiply that by 1/3. Multiply that by 1/3. So 6 times 1/3, that would be 2. Negative 6 times 1/3, that would be negative 2. What about the x's? Well, every x got replaced with negative 1x. So every x has to be multiplied by negative 1. That times negative 1, and that times negative 1. So 6 times negative 1, that would become negative 6. Negative 6 times negative 1, that would become positive 6. And because it's negative, there's a flip here. So the new boundary box would be, I'll do the x's first. They go from negative 6 to positive 6, and they go from 2 to negative 2. So my box is one that fits nicely into these boundary points, just like that. And then keep in mind that there was a flip. Positive x's became negative x's. So this part of the line went that way, and this one went that way. So now instead of going through the upper right hand corner, it'll go through the upper left, and instead of going through the lower left, go through the lower right. So the line will look like this.
Puppy.
Hold on, Mija, I'm almost done. Like that. And then you could reconcile this with your previous knowledge. If you had done this before you knew these excellent principles that always work for everything, for lines, for parabolas, for hyperbolas, for everything. If you had done this before, you would have probably done something like this. And, well, it goes through the corners. You would have done something like this. You would have done y is equal to negative 1/3 x, and you would have said, hey, that's just y equals mx plus b slope. So slope is negative 1/3, rise over run. You rise negative 1 and you run 3. So you go negative 1 and over 3, negative 1 and over negative 1 and over 3. I told you you'd get exactly the same line, which is really nice that you get the same line. But it's really nice that this principle works for everything, for lines, for trig functions, you name it. Alright. Anyways, that's where we left off last time. What we got to do today is we got to add one more principle to our list of principles. We shall call it the shifting principle. Super famous. And what it pretends to contemplate or to answer or to address is the following. What would happen if you replace x with, say, x plus 3? What will that tiny little tweak on the equation, what will that little tiny tweak do on the graph? That's what we intend to answer. Or there's nothing special about 3, or you could replace y with y plus 1. What will happen to it? That's what we got to answer. If you replace x with, say, x plus or x minus 1, what will that do to the graph? Of course, the name of it sort of gives it away, since it's called the shifting principle. Guess what it's going to do? So, as usual, when we don't know what the consequences are on something, we can always go back to the very always consistent method of plotting points. So replace x with, say, x plus 1. Let's try to explore and think about what would that do to the graph. Replacing x with x plus 1. As is, x plus 5, that would be the graph of this line right here, x equals 5. Okay? This we don't know yet. We don't know what that does to the graph when we replace x with x plus 1. So what we could do is rewrite the equation here and we could rewrite as x is equal to 4. Now that we know what it is. It's just almost the same as that one, except it's been shifted to the left one. And so that sort of gives you a hint. If you replace x with x plus 1, first of all, this is a horizontal modification, so you'd expect some sort of horizontal move. Indeed, replacing x with x plus 1 shifts it left 1. So every x, for example, you would subtract or you would add a negative 1 to each x value. That's the principle right there. That will tell you how the shifting works. So, and it's not just special to the lines. Oops, excuse me. Sorry. It's not just special to the lines. It would work for every single graph in the world. So here's how it goes. Replacing x with x plus 3 will shift. You will add to all, to every x, you would add negative 3. Here you would add to every y a negative 1. In other words, this was shifted to the left 3. It's always the opposite of what you might expect. This was shifted to the left 3. This was shifted down 1. You'd have to add a negative 1 to every x. This was shifted to the right 1. You'd have to add to each x a positive 1. Always, always, always the opposite of what you might expect. Replacing x with x plus 1 shifts it left. X with x minus 1 shifts it to the right 1. Y, replacing it with y plus 1, down 1. Okay? That's the shifting principle. Now, let us practice that on our functions. For example, let's see how it goes with sine. So, suppose you wanted a graph. Let me see, can you guys see that? Perfect.
Papi.
Yes, mija.
Can I have a paper?
Replacing grab one from the printer, mija. Replacing y with y minus 1, let's see, and say you wanted to replace x with x minus 90 degrees, just for fun. What will this do to this part right here? What will that do to the graph? Well, it'll shift it up 1. So if this is 1 here, you'll have to add 1. If this was negative 1, you'd have to add 1. How about on the x's? Every single x, you'd have to add a positive 90. Remember, it's always the opposite. If this is x minus 90 degrees, you want to add, it was shifted to the right 90 degrees. So if this is 360 degrees, you want to add 90 degrees. If this is 0 degrees, you want to add 90 degrees. So the new bounding box would be 1 plus 1 is 2, negative 1 plus 1 would be 0, 360 plus 90 would be 450, 0 plus 90 would be 90 degrees. So my new box would be start at 90, and at 450, start at 0 and end at 2. So the box would fit somewhere nicely right around there. From 90 to 450, from 0 to 2. And now all I gotta do, there was no flipping going on here, so I just draw it exactly as it's here. I draw it again. And now you see why they pay me. That's it. That's the shifted graph, shifted sine graph. That was so easy. Let's do it again. Want to try it again?
Okay.
Always do the opposite. Let's try a cosine. You guys feel like a cosine? Alright, suppose you wanted to graph, let's say, y plus 2 cosine of x plus 40 degrees. We'll take that, x plus 40 degrees. Here, the way we would look at it is this. This part right here tells you that you're going to shift down 2. This part over here tells you you're going to shift left 40 degrees. Okay? So 40 degrees. So that means that if this, let's look at the values here. Let's do these values carefully. This used to be 1 and negative 1. What do we have to do to every y value? We have to add negative 2. We have to add negative 2. So where would I put the new y values? Think about it. 1 plus negative 2, that would be negative 1. Negative 1 plus negative 2, that would be negative 3. That's shifted negative 1, negative 3. That's shifted 2 spots down. Right? Let's look at the x's now. This piece right here tells you you're going to shift left 40 degrees. So if these were 0 and 360, how do we go left 40? You got to subtract 40 degrees, and you got to subtract 40 degrees. That would put you at 320 degrees and negative 40 degrees. Right? So the new box would be negative 40 degrees and 320 degrees. So I've got to make my box fit nicely right into that area. That would go from here to there. Can you see it? Can you dig it? From negative 1 to negative 3, that's shifted down 2 spots. And from negative 40 to 320, that's shifted to the left. Let's shift it to the left 40 degrees. And now all I got to do is fit the graph nicely in there as it appears there, since there's no flipping going on. Just as it appears there, I got to fit it nicely into this box. Start here. Perfect. Not so perfect. Let me try again. That's not the kind of teacher I am. How about that? A little better. Okay, there you go. A shifted graph for you. Down 2 spots, left 40 degrees. Alright, let's try something a little crazy here from your algebra class. From just basic lines. Hold on. Okay, where were we? Yeah, this one's just for fun. Watch this. Suppose you replace y with, say, y plus 1. And at the same time, you replace x with, say, x minus 2. On the one hand, this part right here tells you to shift down 1. This part over here tells you to shift right 2. So let's do it. We make a note of the shiftings over on this side. Let's just say this box goes from 1 to negative 1, negative 1 to 1. Okay, so then we're going to shift. Let's do this one first. Let's do that one. So that's down 2. So that would be, on this one we have to subtract 1 and then subtract 1. That would put you from 0 to negative 2. For the x plus 2, we have to go to the right 2. So that would be plus 2 there, plus 2 there. And so you have 1 plus 2, that would be 3. Negative 1 plus 2, that would be 1. So the new boundaries go from, let's see, I'll do the top. 0, the bottom, -2, the right, and the left, 1, 2, 3. So the box goes something like that. And so the line goes through that box, and exactly, maybe not exactly, I'll give it one more try. It's pretty close. It goes through the corners just like that. And that would be the shift. Now that part is not that interesting. The interesting thing is that you could, for example, someone came along and said, hey, wait a minute, this equation could be rewritten differently. You could rewrite it to where you subtract 1 from both sides and you have that y is equal to x minus 3. So this equation is exactly, should have exactly the same graph as the other one, but this one's not shifted vertically. This one's just a horizontal shift to the right 3 spots. So you think to yourself, whoa, what would happen if I graph that one? And you know, of course, if everything is to work out as it's supposed to, you should get exactly the same graph. I think it's fun to see how consistent these principles are, no matter how you rewrite the equation. So let's make that be our next example. Suppose you wanted to graph y is equal to x minus 3. This is in fact the same equation, but let's see how it goes. So we go from 1, -1, -1, 1. This one just tells you that you should shift to the right 3 spots. So the only modification on this would be add 3 there and add 3 there. So your new box would go from 1 to -1, add 3 to that, that would put you at 2. -1 plus 3 is 2, 1 plus 3 is 4. So your new boundaries are 1, -1, 2, -1, 2, and 4 over here. And so your box is right around here, and your line is right around here. And you say, whoa, that's not the same line as before. But if you think about it, it actually is. The box is just different. If you were to place the box on the overlapping, it would go from 2 to 4. It would go something like this. That box is exactly the same as that one, and in fact the two lines are the same. See that? The equations are flawless. The principle is flawless. If the equations merit it, then shifting down 1 and right 2 turns out to be the same as shifting to the right 3. Not always, just if the equations merit it. If on the equations you can move that, you can shift this shift from being a vertical shift to a horizontal one, as you can in this equation, bam, no problem. The principles will allow that. The principles are incredibly consistent. Anyways, something for you to think about. I thought that was fun. By the way, you can also try this on all sorts of things. You might have seen it on circles as well. Suppose you wanted to graph, say, x minus 2 squared plus y minus, or y plus 1 squared is equal to 9. You say, well, that's related to the famous equation of a circle. Circle centered at the origin with radius 3, so that goes from 3 to -3, -3, up 3. This one right here tells you to shift to the right 2. This one right here tells you to shift down 1. So to the right 3, to the right 2, sorry. Let's see. Here you'd have to add 2. Here you'd have to add 2. That would put you at -1 to 5. Here you'd have to subtract 1, subtract 1. That would take you from 2 to -4. So your new box would be from 2, -4, from -1 to 5. And so I'll do my best to graph it more or less like so. Yeah, I didn't do such a good job, because it should still be a square. Let me try that one more time. -4. And let's see. That should be a little bit more representative of what it is from. So there it is. That's good. We're going to call that close, good enough. From 2 to -4, from -1 to 5, and all you do, there's no flipping or anything going on here. So all you do is fit the circle nicely in there as best as you can to fit inside the box. And there it is, the shifted circle. Now the center is, even the center got moved, of course. The center used to be 0, 0. It got shifted to the right 2 and down 1. So now the center is at 2, -1. I told you. Didn't I tell you? It works for everything. Alright, so maybe we can just finish off this section with one more example from our trig class. This excellent shifting example. Maybe we can try one of the cotangents or cosecants, or the tangent ones. One of those ones that have asymptotes. Just for fun, because I haven't done that many on here. So let's try one of those. So this time let's try to graph a little shifted tangent, just for fun. Suppose we wanted to graph y, let's say y minus 2 is equal to tangent of, say, I don't know, what do you say we do? Tangent of x minus 60 degrees. Yeah. Alright, so you first look at the modifications. What does this one tell you? You should immediately be aware of what this one is telling you. This one's telling you you're going to shift up 2. Okay? Up 2. This one right here is, you should immediately be aware that this one's telling you you're going to shift to the right. To the right 60 degrees. Okay? So I made a little box here to try to get a hold of the tangent function. The key to the box is going through some famous points that you can use to replicate the graph inside the box. Some of the there's no, there's not one way to do this. You just pick something that you know goes through the graph. For example, I know that for example, if x is 45 degrees, tangent of 45 degrees is 1, so I know this corner is 45, 1. Just by plugging it in here. And I know if it's negative 45 degrees, this one right here is negative 1. Because that's a famous ratio, or famous angle for which I know the tangent function. So this would be a suitable box where the tangent goes through the lower left and upper right hand corners. And of course, some other famous x values on the graph are the asymptotes. This is 90 degrees and this is negative 90 degrees, where you've got your first set of asymptotes that occur from the origin. So let's do it now. Now usually this means every single y you add 2 to it. So we're going to add 2 to this. I'll add 2 and I'll add 2 to this. So that would put me at 3 and at 1. And this one tells you to every single x you're going to add 60 degrees. So and here I've got 1, 2. This is more than just a box. This is box and asymptotes. All of them have x values. 1, 2, 3, 4. All of these I'm going to add 60 degrees. Start off with the left asymptote, 90 degrees, negative 90. If you add 60, that would put you at negative 30 degrees. Next one, negative 45. If you add 60, that would put you at 15 degrees. 45, if you add 60, that would put you at 105 degrees. Next one, 90 degrees. If you add 60, that would put you at 150 degrees. So to every single x, I added 60 degrees. To every single y, I added 2. That's a shift up 2 and to the right 60 degrees. So where would I find my new box? I've got all my values here. My asymptote is going to be at negative 30. My other asymptote is going to be at 150. My y values are going to be at 1, and my y value is going to be at 3. And on my box, my left value is going to be 15 degrees, and my right value is going to be 105 degrees. So first, I'll draw my box. My box would be right around there. Right? From 3 to 1, from 15 to 105 degrees. My asymptotes, they would go through that negative 30 and that 150. And of course my graph has to fit nicely in here. There was no flipping or anything, so all I have to do is replicate this being shifted onto this position. So the graph would go something like this. And of course, this is just one period. You'd have many copies of that. That's how you'd grab a hold of the tangent. Just make a nice box on it and just shift the box. It's the shifting principle. Okay. What do you think? Is it your turn? I think it's your turn to do the homework. Remember,